Hello, today we are going to look at the sample mean and its confidence interval. So we've already looked at the confidence interval for a sample proportion, and this is going to work basically the same way, slightly different formula, but basically the same idea. Now we already know, if we look at our normal curve here, that roughly, this is the empirical rule I've written up here, roughly 95% of our distribution is between two standard deviations from our mean. So what we can use that with, we know that we've gone on from the empirical rule and we now know that it's not plus or minus 2 standard deviations, it's closer to 1.96 standard deviations from the mean. It gives us 95% of our sample. So that allows us to construct our 95% confidence interval by going from the mean out to minus 1.96 standard deviations and plus 1.96 standard deviations away from our sample mean. So this is almost identical to what we would have done with the sample proportion. Now, reminder of some language, we have mu as the population mean, x bar is the samples mean. So we're going to take a sample from the population to get an idea of what the population mean should be. Sigma still stands for the standard deviation. That can be the standard deviation of the population or the sample. They will sometimes give you one or the other, and you use them exactly the same way. N stands for the size of the sample. And E, as we will tend to use it, it is still the margin of error, which in this case is 1.96 standard deviations. Now we can see I've been calling this the standard deviation. This is our standard deviation for the mean as opposed to the standard deviation for, or the standard error for, our sample proportion. So it is our normal standard deviation divided by the square root of the sample size. And that is what we need for our standard error, standard deviation of the sample. Now, so this is what our confidence interval will look like. We are 95% confident that the true population mean, mu, is between these two values. So we get our sample mean, and we subtract away our 1.96 standard deviations of our sample, and then add on the same on the other side. So that is our confidence interval. Now the mean, a lot of sample mean questions, if we're asked about hypothesis tests or anything like that, as we will be soon, they will tend to work with z-scores. So the only time we will tend to use this formula as we're writing it today is if they ask us directly for the confidence interval. So if they ask us directly for the confidence interval, that's when we will tend to use this method for our sample mean. Otherwise, we will tend to use z-scores for our sample mean type questions. Now, let's have a look at some practical application. Find the confidence interval for the population mean from a sample of 225 with a standard deviation of 10 and a sample mean of 20. So we are looking for this confidence interval from mu, our population mean. So let's take this block of English and turn it into some key figures, and then we can write down our formula for our confidence interval, because that's what they've asked us for in this question. They didn't ask us for a hypothesis test or anything like that. They asked us directly for a confidence interval. Now, we start scanning through here. We're looking for the confidence interval for the population. So we're looking for confidence interval of our population. We can write that in to remind us that's what we're looking for. From a sample of 225, with a standard deviation of 10. They haven't actually told us which standard deviation we're dealing with here, whether it's the sample or the population. It doesn't matter. We will treat them exactly the same. So sigma is equal to 10, and the sample mean is 20. So sample mean, we don't call mu, we call x bar for our sample mean, is equal to 20. So that's all of the information that we are given in the question. I know I'm looking for my confidence interval, so let's write down what the confidence interval is. It's going to be our mean plus or minus our margin of error. They could also ask us directly for the margin of error, in which case we just write down our formula here. So we're going to have x bar minus 1.96 on sigma all over root n, and x bar plus 1.96 on sigma all over root n. Now, again, what this means is we are 95% confident that the true population mean is between these two values. And we can see that if our sample got bigger, the plus or minus that we'd be doing would be getting smaller. Our margin of error would be getting smaller as n gets larger. So we would be narrowing down. If we took larger samples, we'd be narrowing down the error, and we would have a better idea of what the population mean would be. So let's sub into our formula. We have x bar is 20 minus 1.96 on sigma is 10 all over the square root of 225 . 20 plus 1.96 on 10 all over root 225. Doing this in two separate steps is a good idea because it allows you to see exactly what the margin of error is. You can calculate it out separately and then sub into this formula as I've written it here if you like. But what we get when we put that into the calculator is 1.3067. It's actually 6 recurring. Mu 20 plus the same thing. So we're adding and subtracting exactly the same thing, and that's actually going to come in for our next question that we're doing here. So it's important to write these things out to try and anchor these things in the more basic questions so it's easier to do in the harder ones. And so then approximately we end up with 18.7 and 21.3. Approximately. Obviously, we know it goes on a little bit more than that. Actually, we could go to 2 decimal places, I suppose. Yeah, two decimal places would be better, and we'll go 6, 9, 3, 1. 2 decimal places would be more of a standard. So again, we are 95% confident that the population mean is between these two values. And if we got larger samples, we'd be shrinking down our plus or minus, and these two would be closer in number. So let's have a look at our standard deviation. Our next question. The standard deviation is 150. What sample size gives a confidence interval of 880 to 930. So let's write down our information. Sigma, again, we're not told what version of sigma we're dealing with, and it doesn't matter if we are, we're still going to treat it the same way. Sigma equals 150. What is the sample size? So we're looking for n. Given a confidence interval is equal to 880 to 930. So our confidence interval for the mean would be our formula again. So that would be x bar minus 1.96 over sigma root n. X bar plus 1.96 sigma all over root n. Now, We aren't told the mean in this case, but there is an easy way for us to figure out what the mean must be, because these are the limits of our, or the boundaries of our confidence interval. We know that the confidence interval comes from adding and subtracting the same thing to the mean. This is one of the advantages of writing this out as two extra steps, or sorry, as one extra step, because it highlights that to us as we're going through the questions. So what we can do is say that halfway between these two numbers would give you the sample mean. So the issue we have at the moment is we want to find n, but we have two unknowns. We have x bar and root n. X bar and n are two unknowns. So we need to figure out what x bar is, and then we'll be able to find out what n is. And it's easy enough to find x bar because we know that it's halfway between these two boundaries, because again, we're adding and subtracting the same thing to x bar to get these two numbers. Therefore, x bar must be halfway between them. So if we get the average of these two, if we get the midpoint of those two, there's a few different ways to do this particular question, and if you prefer to do it a different way, there are more than one way to approach this. And it's perfectly fine if you want to do it a different style of way. So when we do that, we get 905 for x bar, because that's halfway between the boundaries of our confidence interval. So we now know x bar, so we can pick either of these formulas now and set them equal. We could set this equal to this, or this equal to this. I'm going to do the larger one, no particular reason. So x bar plus 1.96 sigma all over root n is equal to 930. And I know what x bar is, and I know what sigma is, and then that's going to leave you an equation that only involves n. So x bar I just worked out is 905 plus 1.96, and sigma is 150 all over what I'm looking for, which is root n, and I know that that's all equal to 930. Now this is just a bit of algebra. We are just rearranging our formula. And 1.96 and 150 all over root n. This is just rewriting it to a way that's a little bit more comfortable. We now need to rearrange our formula here. So I want to multiply both sides by root n, because I don't want that root n on the bottom of my line. I'm looking for root n, so I don't want it underneath the line. So I get 1.96 on 150 is equal to 25 root n. Divide both sides by 25, and I get root n is equal to, where is it? 11.76. Now I don't want to know root n, I want to know n. So we're going to square both sides. I get n is equal to 138.2976. Now, we have to think carefully about this. We want the sample size that's going to give a confidence interval like this. Now, if we rounded this down to 138, we would end up with a larger confidence interval than this. So we have to round up regardless of how small our decimal bit is up to our next number, so that our confidence interval is this or smaller. And that is what we need for now.